Morning, everybody. We're going to finish up our last section on linear correlation today. And what we're going to look at is something that's called Spearman's rank correlation coefficient, which is going to be very much related to the correlation coefficient that we have been talking about, just a different way of looking at it. So we're going to pick up off of page 123 in your orange book. So if you wanted to kind of follow along and look at where I'm getting these tables from and whatnot, you can look there. So what we're going to do first is we're going to look at this table that has 10 different athletes that we're labeling A to J. And kind of what we got going on here is each of these athletes is performing a long jump. And so what we have recorded here is we have their maximum speed that they've ran doing this jump, and then we have the actual length of these jumps here. And so we wanted to, so what I went and did is I ran the regression, the linear regression for this, and found that there is a correlation between maximum speed and longest jump of approximately 0.864. And if you remember from the previous class when we're talking about this correlation, 0.864 is all right. The closer we are to 1, the better. So this is like decently strong, but it's not perfect. And so the thing is, the weaker that R is, the more that we can suspect that there is. The weaker the R is, we can try to look for other models. And so for right now, what we're going to do today is that if we suspect that this data that we're looking at is not linear, we're going to look at how the data ranks rather than just the raw data. And so basically, kind of the blueprint that we're going to do for this, the reason it's called Spearman's rank correlation coefficient, is we're going to rank each of these data values. So we're going to rank the smallest one with a 1 for the X values and the smallest one with a 1 for the Y values. So as we're going through here, and I scan the maximum speed, which is X here, I'd say, okay, the smallest there is 7.28. I'm going to denote that right there with a 1. And this, I'm going to scan the long jumps here, and I'm going to look for what is the smallest one. And so it is right here. So then I'm going to do that for each of these to get a ordered pair that I can plot. So the ordered pair for this coordinate right here would be 1, 1. That's the Spearman correlation coefficient ordered pair that we're going to run a regression on here in a second. And we're going to do that for each of these. So the athlete H here would be denoted the second lowest speed, second lowest long jump. Excuse me. And we're going to go through and write ordered pairs for these real quick. So athlete J would be third lowest speed, third lowest long jump. Athlete D here would be 4 and 4. C would be 5 and 5. Now we run into some discrepancies here because now they don't work out perfectly here. So athlete A is the 6th fastest speed, but they break this trend of being, like you would expect them based off of what we see to be 6, but they actually have the 8th lowest long jump. And so then we look for 7 here. So the 7th speed right here has the 6th long jump. 8 has a 7. 9 has 10. And then 10 has 9 right here. And so what we're going to do with the Spearman's correlation coefficient is we're going to plot all of these points. So I've plotted these points right here. And what we're going to do is we're going to run a regression on those coordinates. We're going to run the regression just like we did last class. Except here we're going to use these ranks. So I'm going to go ahead and punch in through 10 here. 6, 7, 8, 9, and 10. And then we're going to go over here. So it was 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. It was 6, 8, 7, 6. It was 8, 7. We've got 9, 10, and then we've got 10, 9. And we're going to run a linear regression still just to see if the ranks follow that pattern. And so if you look there, we've got a regression of about 0.952. So R is approximately 0.952. And so what that indicates, our initial data said the correlation was like 0.86. So it was not necessarily linear. And what the Spearman's correlation is going to tell us is that there is a strong upward, but not necessarily linear trend. We run Spearman's when we're not 100% certain that it's linear, but we want to see if there's an upward trend or a downward trend in the data, or if it's just distributed randomly. So we're going to look at an example of this here in just a second, but kind of just to recap that. The Spearman's rank correlation coefficient, all that this is you're going to rank your data from smallest to highest. I guess you could do it from highest to smallest as well. And you're going to look and see, okay, we're just going to run Pearson's once we rank these things. So I'm generally going to list these smallest to highest. I'm going to generally list these smallest to highest. If you look at the examples, they will generally be smallest to highest. You will, if you look elsewhere, some people choose to do highest to lowest, but in this course, we're going to do lowest to highest. And so the notation here that we're going to use, if you see R with a little P for it, that stands for Pearson's R, and we're going to use that for just for trends we suspect are linear. Now, we've got Spearman's rank right here that we're going to denote with this R little s, Spearman's correlation, and we're going to use this when we think it's nonlinear, but it's the data is either moving upward or it's moving downward. And what we're going to do is if we have values that are equal, so like if you have some numbers that are tied, you've got to make sure to split that ranking between those two numbers. So if like they were both tied for the 5th and the 6th spot, you say, okay, well, I'm just going to rank both of those 5.5 because we got to split the difference there. Now, so what we're going to look at an example here. This is example 5 in your all's textbook. This is on page 124 if you're wanting to look there. And so what we've got here is we got the population of black bears that's been recorded every 5 years since 1975. And so the first thing that the problem wants us to do is to draw a scatter plot illustrating this data right here. And so I've gone ahead and plotted this data in advance because you all don't need to see me plotting points on a scatter plot. But I do want you to notice the trend of this data right here. If you tried to draw a curve through that, or just a straight line through this, if I try to graph my pen on this, there isn't really a great spot for me to go through all the points. The line of best fit probably wouldn't be great. And so right away, that should be an indicator to you that we're going to use Spearman's rank to figure out, to describe this data rather than a linear model. Because it looks like we're going up mostly the entire time, but there is a little bit of, it's not completely linear. It could be something else. So what we're going to do, first off, is we're going to calculate Pearson's product correlation coefficient, so just the regular R for that data. So I'm going to bring that back real quick just so I can calculate that, make it easier for you all to see what I'm doing. So I'm going to go punch in this list real quick. I wish there was a faster way for me to do this. Like if we're going by fives, I wish we could say we're going by fives to a certain point. So 0, 5, 10, 15, 20, 25, 30, 35, 40. And if you want to fast forward through this part, I completely understand. If you don't want to just watch me punch in numbers, that is perfectly fine. So let's see, 1836, 2678, 3077, 3394, 3501, 3479, 3418, 3511. So when we go in to calculate Pearson's regular R, we go in for a linear regression here. The data here, if we run that regression, again, not super strong here, not the strongest regression that we've ever seen. So that's going to round to about 0.86. So the Pearson's coefficient here is 0.86. So not the best we've ever seen, right? Like it's decently strong, but not the best. And so what we're going to do is we're going to look and say, okay, well, how does the Spearman coefficient work? So to do that, what we've got to do is we've got to create some ranks here. We've got to create some ordered pairs for this data for us to plot and for us to look at here. So 0 is obviously the least amount, and with the years here, they're actually just going to go in numerical order: 1, 2, 3, 4, 5, 6, 7, 8, and 9, because those are going in order. So we're going to look here. I'm going to scan. Okay, my smallest value is there, so that's going to get a 1. Next smallest one is 1830. We'll go 3 and 4 and 5, and then we finally run to a little bit of some mix up here. So 6 is going to be 3,418. 7 is going to be 3,479. 8 is going to be 3,501. And 9 will be 3,511. So what we're going to do is we're going to look at this at these new ordered pairs. So we've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 8, 7, 7, 8, 6, and 9, 9. We're going to look at these ordered pairs, and we're going to see, okay, does the correlation fit better for the ranks than it does for the linear? And if it does, then that suggests that this may not be a linear fit. There probably is a fit, but it's probably not linear. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then over here on the left-hand side, 1, 2, 3, 4, 5, 8, 7, 6, and 9. And we're going to calculate the coefficient for that. So we go to linreg again, we hit enter, and so the Spearman's coefficient for that, the R sub s, is going to be 0.933. So stronger than the coefficient we found up here. So that suggests that data there, if we thought it might not be linear, then we want to roll with the Spearman's here. So what we're going to say is, so which correlation coefficient is more appropriate to use here? And there's a couple things. So the Spearman's the coefficient there can tell us that. Also, if we go back and we look at this scatter plot here, we can look and see that that's probably not linear. So both of those things tell us that we want to use Spearman's here. Data isn't linear shaped, and so we want to roll with using Spearman's. So Spearman's is more appropriate here. And so now the last thing that we want to do is describe the correlation between the variables. Since we're rolling with Spearman's coefficient here, we're going to say, so 0.933 is pretty strong. We're going to say that there is a strong positive, and then the key here is non-linear relationship between the variables. So between the years and between the amount of black bears. Now, we don't know what type of nonlinear there is. There could be an infinite amount of nonlinear graphs possible. The only thing we can say with Spearman's is linear or not linear. So that in a nutshell is what we're going over today, is Spearman's rank correlation coefficient. So if you all have any questions at all, please let me know, and we can get those ironed out either on email or through Zoom. And I hope you all have a good rest of your day. Bye.